All right, so I'm going to walk you through the derivation of the standard form of an ellipse from the definition. And it's going to be a lot like what you did with the parabola construction, but I'm going to be doing all the algebra. I've already typed it all up. I'm just going to explain to you what we did as it went along. But first, let me remind you what the definition of an ellipse is. Remember that in an ellipse, the sum of the distances from the two foci is constant. So what I've done here to make some of the algebra a little simpler is I've centered this ellipse around the point 0, 0. So you remember in an ellipse, the focal length is called C, right? So if I move C to the right of the origin, I land at the point C0. And if I move to the left, I land at negative C0. So those are going to be the coordinates of my foci in this ellipse, which I've made horizontal. I could do it for vertical. We'll talk about the difference in a little bit. And then I've labeled a general point on the ellipse, x comma y. So we're going to talk about the sum of this distance and this distance being constant, which if you remember, we also talked about in class, that sum of the distances is 2a. All right, so here comes the algebra. So the first thing, get my revealer to work here, is I've set up the distances from the general point to the left-hand focus, that's this here, and the general point to the right-hand focus, that's this here. So this is the sum of those distances, and that sum equals 2a. So this is a radical equation that has those two different types of radicals in it. So remember in the last chapter what we did with those is we moved one of the radicals to the other side so we could isolate one of the radicals. So I did that in this step. And you notice also I went ahead and cleaned it up. X minus negative c is now x plus c. Y minus 0 is now just y. So now I have something that I can square both sides. So when I square both sides, remember, on the left-hand side, the square being on this radical will simply cancel the effect out. But on the right-hand side, because I have something added or subtracted from a radical, I'm going to have to FOIL that out. So in this next step, you'll see what I did. I basically canceled out the radical and the square on the left-hand side. And on the right-hand side, I actually FOILed that out using the pattern of a perfect square trinomial. The square of the first, that's this. Twice the first times the second, that's this big term in the middle. And square of the last, and that which gets rid of the radical of this and leaves you with this. So essentially what I have here is a kind of radical equation, but there's only one kind of radical now. So what we did in the last chapter with that is we isolated that radical and went from there. So if I look at these two terms right here, though, this x minus c quantity squared and this x plus c quantity squared, before I do anything else, it looks like if I were to FOIL those out, I'd have some common terms. So I went ahead and did that. Here's this, FOILed out. Here's this, FOILed out. So if you look on the left and right hand sides, I have a lot of terms that are the same. I have x squares on both sides. I have y squares on both sides. I have c squares on both sides. And those can be subtracted from both sides and completely go away. Notice also I have cx terms on both sides. While those don't subtract and go away, they can be combined into one term on one side. So in this next step, that's really all I did, is I subtracted all the things that were alike, the x squares, y squares, c squares, and I moved the cx terms to the left-hand side, so I have 4 of those. Now look at that. Those terms all have a 4 in common. So in the next step, I just got rid of that to clean up the math. Now I have a radical equation with one type of radical in it. And the way to solve that is to isolate the radical and then square both sides. So I'm isolating the radical here, and I did that by moving the radical to the other side just to make the coefficient in front of it positive, and sliding the cx over with the a squared. So now I'm ready to square both sides. So when I do that, on the left-hand side, I FOILed that out because it's a quantity squared. And on the right-hand side, I squared that because it's a product. I can square the a and the radical separately. So I get a squared times the stuff that was in the radical. Well, if you look at those two sides, it's a little bit confusing looking. But if I were to take that x minus c quantity and square it, I would get some stuff that might go away with the stuff on the left. So I'm going to go ahead and do that. This is me FOILing that out here. And then I'm going to distribute that a squared to all the terms that are on the inside. So that's what this looks like. Now this looks like a big mess, but if you look at the left and the right-hand side, you see some things that are in common. This negative 2a squared cx is on both sides and will go away. And then what I'm going to do with the rest of it is the x squared and the y squared. The x and the y are the general points, like coordinates, right? So I'm going to get the terms that have x's and y's of them on the side together, and the terms that don't on the other side. So this is what that looks like. The negative 2a squared cx's went away. I moved the c squared x squared over to be with the a squared x squared. I left the a squared y squared on that side. And anything that didn't have an x or a y, I moved it to the other side, namely this a squared c squared, which is now right here. Now, this looks a little weird, but if you look at the left-hand side, there's a common factor in those two terms. It's a squared. And if you look at the right-hand side on the x squared terms, there's also a common factor, which is x squared. So I'm going to pull those things out, and it looks like this. Now, this starts to look a little weird, because if you look at that thing on the left, there's an a squared and an a squared minus c squared. And then if you look at the x squared, there's part of that there. And if you look at the y squared, there's the other part of that there. So what I'm going to do is take both sides of this equation and divide it by a squared times a squared minus c squared. And that will look like this. Now, when I do that, what's really interesting is on that left-hand side, we now get 1. Right? Because everything cancels. On the right-hand side, in this x squared term, the a squared minus c squared cancel, which would leave me with x squared over a squared. And on the y squared, we get the a squares canceling. So I'd be y squared over a squared minus c squared. So if I look at that, that gives me this. And that is really close to being pretty. The only thing that's weird is we have this a squared minus c squared sitting here, right? So if you think about what a squared minus c squared is, though, in an ellipse, c squared equals a squared plus b squared. So if you get the c squared on the other side with the a squared, and you move the b squared over, you find that a squared minus c squared is actually b squared. And there is the standard form for an ellipse that's horizontal, centered around the origin. Now, if I had started with the foci being vertical, then all the c's would have been the y stuff. And that means that the a squared and the b squared would have switched places in this equation. So the a squared would have been under the y squared, and the b squared would have been under the x squared. And likewise, if I had centered this around any point other than 0, 0, I would have ended up with x minus h quantity squared and y minus k quantity squared. And if you think about it in terms of transformations that we learned before, that makes sense, because shifting it causes you to subtract the stuff from the x and the y, right? So this is the standard form of an ellipse centered around the origin. Now, I'm going to refer to this later when we get to the hyperbola, so it's kind of important to understand what's going on here, but you don't have to be able to recreate it. That's it.